So we were saying that in here we have a polar bond. In here we have another polar bond because it's the electronegativity of the force of attraction of the oxygen over that pair of electrons is different from the hydrogen. Yes? And actually we're going to see that later. So we are going to have a molecule that is bent, like you can see here, and also we have a single bond here and a single bond here that are not aligned. That makes this molecule a polar molecule. So it has polar bonds, yes, and also the molecule itself is polar. Why is polar? Because it has this pair of electrons here that bend the molecule. So we are going to have two single covalent polar bond. So you can see that not only the bonds are important, but also the shape of the molecule is going to affect the polarity of the molecule. Yes? How do we represent the display formula for water, guys? Oxygen, yes. 1, 2, hydrogen, hydrogen. And then remember to put the lone pairs because those occupy space. Okay? And what about the molecular formula? H2O. Good? Now, let's do the last one for this kind of compounds, and then we're going to see the properties of those. Let's do carbon dioxide. Okay? So that was one of the molecules that we did the other day. So I'm going to put carbon here. And then I'm going to put the oxygen and the oxygen in the other side. And we saw the other day that this was actually the shape of the carbon dioxide. So I'm going to move it a little bit so we have the same thing. So I have oxygen here, and the carbon in the center. Yes? Now, how many bonds did we do last time that we did this one? 2. So they were 1 and 2 here, 1 and 2 here. So there were 4 electrons inside one part of the Venn diagram or the dot and cross diagram. And here we have the same thing. And then the carbon, does it have any more electrons? No, because we already put 4 and those are the 4s that it has. Yes? So in this case, I'm going to have 1 and 2, 3 and 4 more for the oxygen, and 1 and 2, 3 and 4 for this oxygen. Is that okay? So everybody completed the octet. Everybody is happy. And now we are going to analyze what kind of bonds they have. What kind of bonds they have?
2 double bonds.
2 double covalent polar bonds, yes? So they have 2 double covalent polar bonds. How do we know if it's polar or it's non-polar? Well, we can see that the carbon and the oxygen are different in general. And we are going to see that in a few minutes. In general, when you are more to the right of the periodic table, you are going to be more electronegative than the ones that are on the left. The more you go to the upper right of the periodic table, the more electronegative it's going to be. It means that it's going to pull the electrons with more force. If you look at the periodic table at the very top, you are going to see that fluorine is the most electronegative. Now, why do I say fluorine and no helium, for example?
Since helium is a noble gas, it's already completed.
So it's not going to form any bonds. That is exactly the reason. the electronegativity is the force of attraction over a pair of electrons that is shared. So the noble gases do not share electrons. That's why we cannot talk about the electronegativity. Can you open the door for Kimberly, please? We cannot talk about the electronegativity of noble gases just because they don't combine with anything. Yes? Actually, that is not completely true. Some of the noble gases combine, but at this level, they don't combine. Okay? Anyways, let's analyze what is going to be the dipole moment. Another word. The dipole moment is going to be kind of an arrow showing where the moment or where the electrons are going to be shifted to. Yes? So in this particular case, I can see, for example, in this one, in the water, I'm going to say that the polar moment is going to be represented as this. Why is that? From here, the electrons are pulled away from the hydrogen to the oxygen. Why? The oxygen is on the right of the periodic table, and the hydrogen is on the left. Yes? So in this case, I have another dipolar moment. And we represent that with an arrow that has kind of a cross in the beginning. Is that okay, guys? Okay, so we are going to do the same thing for this one. Who is more electronegative, we said? This carbon or this oxygen?
The oxygen.
The oxygen, because it's to the right of the periodic table. Yes, actually I'm doing the things backwards. It's to the right of the periodic tables. Okay, so if you see the carbon and the oxygen is on the right of the periodic table. That means that we are going to have this one with a dipole moment on the right. Yes? Now, you have another oxygen here and another carbon, and they are sharing exactly the same amount of electrons. Do you think it's going to be the same dipole moment or a different dipole moment?
I would say a different one.
A different one. Why different?
Because you're going that way.
Because the direction is different. But what about the length of this arrow? Should be the same or different?
Same.
The same, because the amount what they are pulling, yes, is the same but in different directions. Is that okay?
Yeah.
So this is kind of a tug of war. So if you think this one as a tug of war, in which direction this is going to move? I mean, the electrons are going to move.
It's going to stay.
They are going to stay where they are. So although we have two double covalent polar bonds, the shape of the molecule makes the carbon dioxide non-polar. Yes?
Yeah.
Because the electrons are going to be distributed evenly around all the atoms. Now you can see here in the water that this dipole moment and this dipole moment do not cancel each other. Yes? They are like vectors in math. So they don't cancel each other. That's why the water is a polar molecule. Yes? And what about the hydrogen chloride? We have a dipole moment. In which direction do you think it's going to be? To the right. Very good. Okay? So we represent it like this. In this case, we don't have any dipole moment. Exactly. So far, so good? Let's analyze the last one, but we are not going to do this. We're going to do the one that we did the other day, the ammonia. So the ammonia was like this, and we said that the shape of the molecule was like a pyramid, yes, with the electrons here, and we had the hydrogens around it in the space, yes? So what do you think is going to happen? Is it going to be, first of all, the bonds here are polar or non-polar between hydrogen and nitrogen?
Polar.
Polar. So this is a polar, so it's going to have a polar moment here, a polar moment here, and a polar moment here.
Unless you guys stop, the video's gonna end.
Yes. But in this case, the molecule is polar.